Hi, everybody. It's Mr. Neff. Here are my solutions to that problem set on equations of kinematics for constant acceleration. Number 41 has this velocity versus time graph, and it wants to know how much distance is covered by this skater between 0 and 2 seconds and 2 to 5 seconds. Okay, so on a velocity time graph, the area underneath the graph will show you the displacement, and since we're not really changing our direction here, this will show you our distance as well. I actually shouldn't say that not changing our direction because we do change our direction up there at 4 seconds, but I'll cover that in a second. So part A, the distance between 0 and 2 seconds, so it's equal to this area right here, which in the end is just nothing more than the area of a triangle. And so that area is one half the base times the height. And so that's going to be 1/2 times 2 seconds times a height of 2 meters per second, which is just going to be 4 meters times a half, 2 meters. They only wanted distance, so we'll go there. Had they wanted the displacement, that is it's positive displacement because it goes along with positive velocity, so that would have been positive 2 meters, but that wasn't what they asked for. Now, between 2 and 5 seconds, distance-wise, we have this odd shape over here, and you want all of this area underneath here, but I think it's easier to split that up into some shapes. So maybe I'll split up into that, which is a rectangle that's 2 seconds times 2 meters per second, which is 4 meters. And then you have this triangle up here that's a half times 2 seconds times 0.5 meters per second. So that would be 0.5 meters. Then over here, you still have distance covered, but it is a negative acceleration. Still positive velocity, so you're still going forward, but it's going to be a velocity that's not as positive as you go. Notice, though, you don't ever get down into the fourth quadrant, so it's not like it's a negative velocity. Anyhow, this area right here is going to be 1 second times 1 meter per second, which will result in 1 meter. And then this area over here is a triangle, so it's a half times 1 second times a height of 1.5 meters per second. And so that's going to be 0.75 meters. Now, that was all in the same direction, so even if it wasn't in the same direction, they only want distance, so I'm going to add it all up. But this number is going to be good for the displacement too. 0.75 meters and 1 meter. So add that all up, and I'm going to get 6.25 meters. Significant figure, I should probably rounding that to 6. 66 says, if the velocity of a ball is 0 at a given instant of time, can its acceleration at that instant be positive? Yeah, absolutely could. Say you took a lightweight ball like a ping pong ball and you threw it to the left, so it had a negative velocity. But say there was wind blowing this way that was constantly hitting the ping pong ball, and so it's going to push on the ball to the right, and so the acceleration is going to be something to the right, so something positive. So then what's going to happen? The velocity you gave the ball maybe is pretty big, but then a second later it's going to be smaller and then smaller yet, and eventually the ball's going to stop. At that point, that's not going to last. Then it's going to start going the opposite way, and it's going to get this big and then this big, and it's going to undo itself, right? And the graph, if I want to show you that on a graph, velocity versus time, it would start off pretty negative, but then the acceleration would be constant. And as long as just say the wind was nice and constant. Anyway, so yeah, this is an example where we do have 0 velocity right here, but we don't have a 0 acceleration. It's only at 0 for an instant, but the trend just keeps on continuing. It's gonna start blowing the other direction. 67 says if the velocity of a ball is positive, meaning it's going to the right, can its acceleration be negative? Sure it can. Anytime a ball is moving to the right but it's slowing down, I mentioned the wind on the last one. Maybe the wind is blowing this way now, and so that would push to the left, and so the acceleration would be negative something. Well, the acceleration is negative, but the velocity is positive, so can it happen? Yes, and this is what is happening every time something's moving to the right but slowing down. So the answer is a definite yes. 68 says an object has a position versus time graph that is a straight line with a negative slope. Maybe it's this, maybe it's this, maybe it's this, I don't know, but they all have negative slopes. Is the acceleration of this object positive, negative, or zero? So the slope of a position time graph is the acceleration. So when they told you that we had a negative slope, well, that was just as good as them saying we have a negative acceleration. So these all have a negative acceleration because they have negative slope. Here it says a jet is making a landing due east with a speed of 115 meters per second. If the jet comes to rest in 13 seconds, what are the magnitude and direction of the average acceleration? Okay, so a good starting point on a lot of these problems is to write down your 5 possible quantities for a kinematics problem. The jet is starting off at 115 meters per second, and it's coming to rest. And that's happening in 13 seconds. And since I have 3 things filled in here, I can get the other 2. What is the acceleration? So now we go over to our formula sheet and we see that acceleration is change in velocity over time. There's a lot of things on the formula sheet, but I picked this one because it does not have a delta x in it. So I'll say that we start off with 0 and, we end with 0 and we start off with 115 meters per second. And I'll take that and I'll divide by my 13 seconds. That's going to give me an 8.8462. Of course, not all of those are significant. Only 3 of those are significant. Meters per second per second. We can round that to 8.85 meters per second squared. And the whole thing was negative, which makes a lot of sense because you're going from a positive 115 down to 0, so you have to be taking velocity off every second, and there's how much you are. 72 has a skier starting from rest, so initial velocity of 0, accelerating down a slope at 1.2 meters per second squared. They don't tell you that that's the acceleration, but the unit's a tip-off that it is an acceleration. How much time is required for the skier to reach a speed of 7.3 meters per second? Now, you might be tempted to make everything negative because it's down the slope. But since everything's down the slope in the same direction, I'm just going to call that down the slope direction. I'm going to call that the positive direction. If that bothers you, it's okay. Go ahead and make that negative, and you just make these numbers negative. Okay, so there's no displacement in this problem. So we're just going to say acceleration is change in velocity divided by time. And so they want to know how much time. So the time is going to be the change in velocity divided by the acceleration. So the final velocity is 7.3 meters per second. The initial is 0. And the acceleration was 1.2 meters per second squared. You can get a pretty good ballpark for this in your mind, right? 7.3 divided by 1.2 is like 6-ish. 7.3 divided by 1.2 is 6.08, lots of 3s. And that's going to be in seconds, meters per second, times the reciprocal, seconds per meter, cancel like that. Just give you seconds. Only 2 of those digits are significant, so let's round this to 6.1 seconds. Here's 75. A motorcycle moves according to the velocity time graph shown here. Find the average acceleration of the motorcycle during segment A, segment B, segment C. Remember earlier in the video that I said that the acceleration is the slope of the velocity time graph. So all I have to do is find those three slopes. So for segment A, the slope is, well, we're rising 10 meters per second, so rise over run, that's a positive 10 meters per second in a time of 10 seconds. So we're going to make that 1 point. I'm going to call those two significant figures. I don't know if that's, if the authors would want me to do that, but I want to. So positive 1.0 meters per second squared for A. For B, doing the same thing. This is a negative rise. I'm going down by 5 meters per second, and I'm running 5 seconds. So I'm going to make that negative 1 meter per second squared. And then in section C, I have no rise, and so that's going to be 0. Strictly speaking, over 10 seconds gives you 0. And then on number 96, it talks about the position versus time graph of an object with constant acceleration. It says it starts off with positive slope. I don't really know where to put that. Maybe I'll just go right here, positive slope. And then later, the slope becomes negative. So I don't know where to put that either. Maybe I'll just go there like that. The slope is negative. Is the acceleration positive, negative, or 0? Is the initial velocity positive, negative, or 0? Well, they told me already that since this has positive slope, the slope on a position time graph is position time graph. Well, that is the velocity. So that positive slope says we have positive velocity initially. Now, it said we have constant acceleration, so that means we're going to have a curve, but it's going to be a smooth curve. And so to connect these with a smooth curve, it's going to have to be, something like that. So you can see that we've got something that has positive velocity there, and it's a decent sized positive velocity, I guess. And then we have a smaller positive velocity. And then we actually have a 0 velocity. Why am I saying that? Because a tangent line there is 0 versus a tangent line here is less steep. Over here, now it's starting to get steeper again. So we have a small bit of negative velocity. And then over here, that first one I drew, bigger positive velocity. So here's my point. Looking at that first half, you could say we have positive velocity, but slowing down. See, the trend is big velocity, less velocity, 0. So those two things combined say anytime you're slowing down, the acceleration has the opposite sign of the velocity, so we have a negative acceleration there. And if you wanted to look at the other side, you want to look over here, you could say, all right, well, we have a negative velocity, but we're speeding up. And anytime you're speeding up, you know that the acceleration has the same sign as the velocity. So I don't care which side you get it from, you're still going to see that we have a negative acceleration, and we just remember we did have a positive initial velocity.